In this lecture, we'll continue our discussion on Introduction to Thermodynamics. In the previous lecture, we have introduced thermodynamics as the science that deals with energy conversion processes and the properties of substances that are related to these energy conversion processes. And we've seen example of 3 engineering equipment where such energy conversion takes place. We've seen the example of a steam power plant, we've seen the gas turbine, and we've seen the vapor compression refrigeration cycle, which is used in the domestic refrigerators. Now, let's look at another example where such energy conversion process takes place, and then we can go into more details of what is thermodynamics and why do we need thermodynamics and what does thermodynamics give us. So this example is of a liquid propellant rocket engine. A liquid propellant rocket engine is shown in this schematic over here. So it consists of 2 tanks, one which is filled with liquid fuel and another that is filled with an oxidizer. So the example of a liquid fuel can be liquid hydrogen and oxidizer is liquid oxygen. And hydrogen and oxygen are used in liquid propellant rocket engines, which are more specifically known as cryogenic engines. So what happens in a liquid propellant rocket engine is that fuel and oxidizer, which are liquid, are pumped into this combustion chamber using these turbo pumps. And these fuel and oxidizers, they undergo combustion in this combustion chamber, and as a result they produce high pressure and high temperature products of combustion. So these are high pressure and high temperature products of combustion. These combustion products are thereafter expanded in a nozzle which has this converging and diverging profile, and this nozzle is called the converging and diverging nozzle, and this results in exhaust gases which are thrown out at high velocities, and that provides the thrust. So in a liquid propellant rocket engine, you also need power to operate these turbo pumps, and that comes from an auxiliary power unit which also operates on burning some of this fuel and oxidizer. So part of the fuel and oxidizer are used to run the auxiliary power plant that runs these turbo pumps, but major part of fuel and oxidizer is pumped into this combustion chamber where these gases react to produce high temperature and pressure combustion products which are expanded in this converging diverging nozzle. So in a typical rocket, most of the space is actually occupied by these fuel and oxidizer tanks. And liquid hydrogen and oxygen are not the only combinations of fuel and oxidizer, there are many other combinations. But it turns out that liquid hydrogen and liquid oxygen will produce the maximum amount of thrust. They are the most preferable ones. And why is that so? Thermodynamics allows us to answer such questions. Now, with these examples, we can now start looking at what is thermodynamics. So thermodynamics is another branch of science, just like mechanics and electromagnetism in physics, but thermodynamics is a bit different. So unlike mechanics and electromagnetism, which apply to specific systems, thermodynamics is more general one. So thermodynamics is the most general of all the branches of physics, and in fact it applies to all types of systems provided, and this is important, provided they consist of aggregates of a large number of particles. And this is where thermodynamics comes into picture. So thermodynamics is applicable to different kind of systems. These systems may be mechanical, they may be electrical, they can be magnetic, and they could also be chemical or even electrochemical systems. And the only criteria is that they must consist of an aggregation of large number of particles. Now, for example, let's say consider this box in which we have a few particles which are moving here and there. So motion of these particles can be described by laws of mechanics if we know how these particles interact with each other. And of course, mechanics allows us to predict the state of the system at the next, let's say, time. So clearly, for small number of particles, we cannot apply thermodynamics. But if we have very large number of particles, then we can see that such problems, although theoretically can be analyzed by mechanics, let's say, but they are preferable and more easily handled by thermodynamics, and that is where thermodynamics comes into picture. Now, the way thermodynamics is different from, let's say, mechanics and electromagnetism is that thermodynamics as such does not define what we can say a new fundamental law. Of course, there are some laws of thermodynamics, but what I mean over here is that in thermodynamics, we do not have laws which will allow you to give a quantitative prediction of certain quantities. For example, the study of mechanics is governed by laws that predict dynamics of particles when acted upon by forces. Electromagnetism deals with dynamics of fields that leads to such forces. Now, in mechanics, we can predict, let's say, given the force, we can predict the velocities or the momentum of these particles. But thermodynamics does not predict specific values of these observable quantities. Instead, what thermodynamics does is something different. So thermodynamics does not give us the specific values of observable quantities. So thermodynamics does not give this. Just like you can predict momentum or velocity of a particle acted upon by force using laws of mechanics, by thermodynamics we do not predict the specific values. But what we get from thermodynamics are not equalities but inequalities. So thermodynamics will allow us to provide limits on permissible energy conversion processes. And in addition to this, it also establishes the relationships between the properties of substances that undergo these energy conversion processes. And we'll go into these details further in this course. So before we discuss further, I think it is really important to see what great physicists think or say about thermodynamics. So Arnold Sommerfeld says that in a way thermodynamics represents what is common to all the laws of nature, and that's why it applies to mechanics, electrical systems, magnetic systems, chemical systems. And that is why, unlike classical mechanics, thermodynamics has withstood quantum revolution. So even with advent of quantum mechanics, the applicability of thermodynamics still holds, because thermodynamics applies to anything, and the only criteria that we have is that there should be a large aggregate of particles, and that is when thermodynamics becomes applicable. Einstein says that thermodynamics is the only physical theory of universal content which, I am convinced, within the areas of applicability of its basic concepts will never be overthrown. So again, this is an important concept, that within the areas of applicability of thermodynamics, whenever you have such large systems, the thermodynamics will apply to any of such system which consists of large number of let's say, particles. So that's why thermodynamics is a more general science that represents, that is, everything common to the laws of nature, and it applies to any systems. So even though this course is being taught to mechanical engineering students, where we are more concerned about how to use, let's say, fuels or heat to generate mechanical work, or to do mechanical work to transfer heat from, let's say, low temperature region to high temperature region. But thermodynamics is applicable to vast number of systems, and one should not limit yourself to thinking that thermodynamics is only applicable where heat is converted to work, or vice versa. What thermodynamics allows us to do? So thermodynamics has two main applications. Firstly, it provides limits on permissible processes, specifically the energy conversion process. So this is the first application. For example, let's go back to the example of our liquid propellant rocket engine. So what we can say is that in this engine we have this reaction, H2 plus half O2 gives H2O, and in this case the product of combustion is water. So one might be interested in what is the velocity of the exhaust gases that one can attain over here. So what thermodynamics tells you is not the velocity that you would get in a practical engine. What is the velocity of exhaust gases that you get in a practical engine? But what thermodynamics will tell you is the maximum possible velocity. So this maximum possible exhaust velocity may never be achievable in any rocket engine due to departure from ideal behavior, but sets a limit on the exhaust velocity, and it says that in practice your velocity cannot be greater than this maximum possible exhaust velocity. Okay, so that means if you are going to design a rocket engine, then you don't need to go into the details of different components, and thermodynamics does not require detail of different components and how these components work or what these components are made of. For example, how this turbo pump works, how this turbo pump is constructed. That is not what thermodynamics deals with. So thermodynamics deals with a broader picture, that if I have this fuel and oxidizer, then what is the limit of the velocity that I can achieve. So in a way, thermodynamics does not tell you what you can do, but thermodynamics tells us what we cannot do, and that is how it differs from other laws of physics. So thermodynamics always deals with inequalities. Thermodynamics tells you that you cannot achieve an exhaust velocity that is greater than the velocity that you would get from thermodynamic analysis. So someone might say that, okay, that really doesn't help me, but indeed it is really helpful, because let's say you are looking for some fuel and oxidizer so that you want to achieve a certain amount of thrust, and that depends upon the exhaust velocity that you can get. And now if you already know that you cannot exceed this particular velocity, then you need not waste your whole lifetime to achieve that high velocity. So that is why performing thermodynamic analysis on engineering systems before actually going into designing the exact components of the system is what is done, because you already have a picture that you cannot achieve a performance greater than this particular value that you get from thermodynamic analysis. So whenever you do a thermodynamic analysis, the way to interpret is that, okay, this is the exhaust velocity that you cannot achieve, or this is the exhaust velocity above which you cannot achieve. Similarly, if you do thermodynamic analysis of a refrigerator and you come up with the rate at which heat is being removed from a cooled refrigerated space, then if you have done thermodynamic analysis, then you can interpret in a way that in practice you will not achieve rate of heat removal greater than the value that you have achieved using thermodynamics, because whatever value that you are going to get from thermodynamic analysis, you are not going to get that in practice. In fact, that is the upper limit, this is the best limit of performance that you're going to get from the system. So that's how thermodynamics differs. It tells us what we cannot do, and that is also important in engineering. Similarly, for example, thermodynamics can tell you that if you have a heat engine, then you'll never achieve 100% efficiency. So if you're designing engines, you should know that what is the limit that thermodynamics imposes, and you should not aim, or you should not claim that your engine is more efficient than what thermodynamics is able to predict. So this is one example where thermodynamics tells us what is the limit on a particular process. Another example that is related to, again, this liquid propellant rocket engine is this reaction. So thermodynamics also tells you in which direction the process will go. For example, you have this reaction over here. So thermodynamics will tell you in what preferable direction this process will take place. For example, hydrogen and oxygen will react to give you water, but at these conditions the reverse reaction might not be feasible. So that is what thermodynamics also tells you. Similarly, if you have a hot body in contact with a cold body and they are able to exchange heat, then thermodynamics will tell you what would be the final state, let's say, and in what direction the whole system will evolve. Okay, that is what thermodynamics tells you, that what this process is feasible or not. For example, if you have these two bodies which are at same temperature, you cannot go back to this state where one object is hot and other object is cold without doing some additional work. So if you just have this system and you leave this system alone without interfering, then this system, which has same temperature, it cannot go back to another state where it splits up into two parts, where you have a hotter part and a colder part. So thermodynamics tells what is permissible and what are the limits on the permissible processes. So besides this application, thermodynamics also provides the relationship between properties of matter that come into picture during energy conversion processes. The properties of matter are connected through subtle relationships, even though these properties might seem unconnected. For example, let's say thermodynamics can allow us to establish relationship between, let's say, heat capacities, isothermal compressibility, and coefficient of thermal expansion. Now, these properties might seem unrelated to each other, or what might happen is that you can, let's say, measure some of these properties but not the other one. But thermodynamics allows us to establish relationship between these properties, and these relationships are important, firstly because you can measure some of these properties and get another properties which cannot be measured or which might be difficult to measure. And from these relationship between these properties, they also enable engineers to estimate the limitations of a particular device based on the material properties. For example, going back to the example of the rocket engine, we can ask that what are the best fuel and oxidizer combinations which will give me the maximum thrust. And thermodynamics can help us answer that, and we can find answers to questions that why do we use hydrogen and oxygen, and why is it one of the best combinations of fuel and oxidizer to get the highest thrust. So based on the properties of matter and how they are related with each other, thermodynamics allows us to establish not only these properties and these properties then help us in estimating what are the limitations of a particular device. So that is how thermodynamics is helpful for engineers. For physicists and chemists, properties of matter are also important, because if you know how these properties of matter are related with each other, then whenever you get a new material, you should not consider that as a separate problem. For example, let's say you are interested in finding out how the boiling point of, let's say, a liquid, or let's say boiling point of water changes with a change in pressure or increase in pressure. Then from thermodynamics we can get a relation which we may see later on, called the Clapeyron equation. And this tells us that if we change pressure, how the boiling point is going to change. But now if someone asks a question that I want to know how the boiling point of ethanol, or let's say ammonia, or some other refrigerant is going to change with the change in pressure or increase in pressure, then we need not consider that as a separate problem, because the same relationship between the properties are valid, and we can use the same relation with different absolute value of the properties. And for example, we can use the same Clapeyron equation to describe how the boiling point of different liquids is going to change. And that's why this thermodynamics is important even to physicists and chemists. Now, to summarize, thermodynamics differs from other branches of physics because it's more general one, and it is applicable to almost all systems, provided they consist of large aggregate of particles. And we've also seen that, unlike other laws of physics, thermodynamics does not give us the quantitative estimate of observable quantities, but what it does is it provides limits on the energy conversion processes, and instead of equalities we get the inequalities, or thermodynamics tells us what we cannot do. And we've also seen that thermodynamics allows us to develop a relationship between different properties of substances. So through the study of thermodynamics in this course, we are going to discuss both of these applications. We are going to look at the limits that thermodynamics imposes on energy conversion processes, and we are also going to look at relationship between different properties of substances.